are going to be looking at how we can expose functions that are written in C++ to being called from Blueprint using the UFUNCTION preprocessor directive. So let's dive in and see how it's done. The first thing we're going to do is have a look at our scenario. So here we've got our BP grabber. We're still working inside of that. And I want to give you a better idea of how this grabber actually works if you haven't already poked around inside it for yourself. Now, the idea of the grabber is that it's a component. You put it on an actor and you point it in the direction that you want it to grab at things. It has a scene component, so it has a location in space. You point it in the right direction, you put it in the right place, and then you hit the grab button, or basically call the grab function. So let's have a look at what this grab function does, shall we? The first thing it does is it does a ray trace for any physics bodies in the scene and returns conditionally whether there are some actors or not, or a component that has been hit. Then what we go on to do is we set it to simulate physics if it wasn't doing so already, so that it can wave around in the air. This is particularly useful with the axe, which actually starts off hit and stuck inside the wooden block. But that's a detail. Don't have to worry about it too much. And then it grabs the component using a physics handle component, and it centers that on the center of mass of the component that we hit. And then finally, it notifies any quest actors that we've grabbed something, such as when we grab the axe. Now, let's have a look at the trace for physics bodies. That is not a built-in function that is defined here in the BP grabber. It's one of the private functions that don't get called from outside of this class. Now, what's going on here is we're doing a sphere trace for objects. We're starting at the location of this particular scene component, and then we're going to this get max grab location, which is calculated using our max grab distance, which we've moved over into C++. And the reason we moved it over in C++ is so that we can move this function over into C++. We can go in and have a look at the function. It's a fairly straightforward maths function. This is the kind of thing that would be condensed down into C++ very easily. It'll be very legible. In fact, it will probably be a one-line and use far less space than this. So let's head over to the C++ where we can create a function for this. I'm going to create my functions above the variables, and I'm going to add it to the protected section we've already got up here where we've got a begin play. And we're going to have a U function because we want it to be callable from Blueprint. And again, we've got some access specifiers in here that I'm going to talk about in just a second. And then we want to write the signature of the function. What is the signature of the function? Let's have a look. If we click on the node of the function, either here or in the My Blueprint, then what we can see is that it has no inputs, and it is checked off as a blueprint pure, meaning that where it is called, if we go back to the call site of trace for physics, you can see that it has no execution pin. That's because it is a pure function. It just simplifies things in the blueprint, especially when it doesn't matter what order it gets executed in, because it's essentially a C++ const function. So if we go back to our get max grab location, you can see it does have an execution pin in here, but that's really not very necessary because everything inside it is also a pure function or a pure node. So what we're seeing is that actually the return value is a vector. Now, the question is, what is a vector in terms of C++ types? Let's answer the question of what the common types map over to in C++. Let's start with the fundamental types. The fundamental types are things like floats, integers, and so on. Now, float, as we've already seen, maps over to a C++ float. That's pretty straightforward. What about a double, I hear you ask? Well, actually, that cannot be represented in Blueprint. You have to use a float if you want it to be accessible from Blueprint. You can use doubles elsewhere if it's just going to stay within the C++ domains, but this is an area where Blueprint makes a simplifying assumption and assumes you're not going to use doubles. Similar simplifying assumptions are that you aren't going to use unsigned integers in Blueprint. You only use signed integers. So in C++, we have both int32 and uint32, as well as int64 and uint64. But in Blueprint, we've only got the integer and the integer 64, and bool is a pretty straightforward mapping. Now, what about the utility types? These are things like string, name, vector, rotator, transform, all the kinds of things that you see in the drop-down on any Blueprint type. You can see you've got all our basic types like booleans, bytes, integers, floats. Then we've got names and strings and text and vector and rotator and so on. Well, these in C++ tend to have the prefix f. In fact, most struct types seem to have the prefix of f. So we have fstring, fname, fvector, frotator, and ftransform, all things provided for us. So that kind of answers our question, but I'm going to go on just a little bit longer and show you about object types. So things like if you had a UObject reference or an actor reference or an actor component reference, scene component reference, so on. In C++, these would be pointers. So you'd have a UObject pointer, an A actor pointer, a U actor component pointer, and you can see the prefixes coming in. Most things derived from UObject will have the U prefix, and unless they are an actor, in which case they have the A prefix, and that's just a straightforward thing that you will see all around the place. So that hopefully answers the question. We want our return type to be an F vector. It's not going to be a pointer because it's just a struct, and it's going to be F vector, what we're going to call it, the get max grab location. And, well, because this is C++, we know that we can make this const, because actually we don't want it to be able to modify the contents of this class. And then we want to put some keywords inside our U function so that we can make sure this function is callable from Blueprint. The first one is Blueprint callable, and no extra credit for figuring out what that one does. It makes it callable from a Blueprint graph. And if we want to check off that little check mark of pure, then we can use also Blueprint pure. And that just does exactly that thing of making sure there's no execution pin when we call this in Blueprint. So finally, we have to go ahead and actually implement something here. So I'm going to create a copy of the signature to the clipboard and go over into the C++ file. By the way, I used Control-K, Control-O to do that in Visual Studio, if you don't know that already. And I'm going to go ahead and stick this below the tick component. And at the moment, it's just creating a default F vector to return. That suits me for now, and we're going to fill out the function in just a bit. So once you've compiled and you go over into Blueprint, you'll notice that we now have a Blueprint compile error, and that is saying that the function name getMaxGrabLocation is already used and is not compatible with the parent function because we haven't said that the parent function is virtual. We haven't said anything about being able to override it. So it's not happy. Blueprint's saying we can't have two functions of the same name, and it's darn well right. So if we right-click on that getMaxGrabLocation and find references, we want to go and replace those references with the new getMaxGrabLocation. Now, it may have actually already done that. So I'm going to go ahead and delete the getMaxGrabLocation, and you can see that the node calling to getMaxGrabLocation seems to be in place. Let's just go ahead and compile, and it seems to be working. We can go ahead and test the grabber by going into the village, right-clicking and playing from here, and if we go and try and grab one of the pumpkins, it's not going to work. Obviously, because I haven't filled out our grab location. So how do we want this to actually work? Maybe I have prematurely deleted that function. So I'm just going to undo so that we get our function back, and we can just have a look at it. So what it's doing is it's getting the world location and summing that with the get world rotation, the forward vector of the world of rotation of this scene component, multiplied by the grab distance, adding it to its current world location. So that's basically projecting forward our forward direction by the grab distance. Now we want to go over and do this in C++. And for the time being, I'm just going to tell you what we need to include and what functions we're going to use. We're going to be looking at how you can figure that out for yourself. So the first thing is getting the world location. Well, this is a scene component. We should be able to call a function on ourselves to do this, and it's called getComponentLocation, not getWorldLocation. So that's slightly confusing, but there you go. And what we want to do is we want to sum that with the result of this multiplication. So we want to get the forward vector of the getWorldRotation, which again is going to be a getComponentRotation, which returns, if we hover over it, is returning an F rotator, as we would expect, because the return value here in Blueprint is a rotator. And we are going to use a library called the Kismet Math Library. So that's going to be hash include Kismet/Kismet Math Library.h. So that should give us access to a static object called the uKismet Math Library. And using : we can access one of the static functions in here called getForwardVector. And getForwardVector takes in an F rotator and returns its forward vector. So that's exactly what we want. Let's just rearrange our formula here a little bit. So we've got a forward vector that we're adding to our component location. All that remains to be done is for us to multiply that by our max grab distance, which is already in C++, so we easily have access to that. And finally, we just want to be able to return that result. So just as I said, this big function over in Blueprint has condensed down to a one-liner in C++. Let's save and compile that. And also, while we're at it, go and delete our getMaxGrab location again. Now, once the compilation is complete, let's compile and save our blueprint, check there are no errors, go back to our main map and play from our village. Walk up to a pumpkin and see if we're able to grab it. Yes, we are. So we have successfully been able to migrate a function from Blueprint to C++ while retaining all the calls to it that already existed in Blueprint. We've seen how the UFUNCTION macro has enabled us to add some of the metadata that Blueprint needs, and we've seen how we can map Blueprint types over into C++.